Kia ora class. Okay, so today we're doing the 2020 Level 2 Organic Chemistry paper. So, opening it up, first question. We've got a question here about naming and drawing. Here's a mistake I made when I previously did this, so we'll start again. Bute means it's got 4 carbons, so we'll put those in. Carbon, 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 carbon. Amine, 2 amine. So on the second carbon we'll put an NH2. That's the amine group on the second carbon. Let me just fill these in. That's a CH3, that's a hydrogen, HH, and that's a CH3. Okay, we've got an alcohol group here, and we've got 5 carbons. This is going to be a pentan 2-ol. Ol for the alcohol group, 2 on the second carbon. Okay, we've got a couple of things going on in this one here. First of all, 1, 2, 3, 4, 5, 6 carbons is our longest chain, so it's a hex. The double bond there between the second and the third carbon tells us it's a hex 2-ene. And we've got this methyl group off the second carbon, so it's a 2-methyl hex 2-ene. Iodoethane. Okay, eth meaning 2 carbons. Iodo meaning it's got an iodine on it, and then just fill in the hydrogens. Alright, classify the alcohol in the table above as primary, secondary or tertiary. So this alcohol here, we're classifying it as a secondary alcohol because the carbon that the alcohol group is attached to 1, 2 other carbons. Carbon, I should say that the alcohol. Okay, the carbon that the OH group is on is attached to other alcohols. They're attached to other carbons. Okay, depending on the conditions in which it is used, sulfuric acid can enable 2 reactions to occur. You can go alcohol to alkene or alkene to alcohol. Okay, so just looking at these equations here, these reactions, the alcohol to the alkene, that's an elimination reaction. And the alkene to the alcohol, that is going to be an addition reaction. So I know that already. Okay, in the boxes draw the structural formula model containing 2 carbons that could be used in the reactions above. So a 2-carbon alcohol, easy. 2 carbons in the OH group, and then we'll just finish it off with hydrogens. And a 2-carbon alkene, so carbon, double bond, carbon, and then do the hydrogens. Elaborate on how sulfuric acid is used in the conversion of both alcohol to an alkene and alkene to alcohol. Okay, we need to talk about the conditions for these reactions. We need to talk about the type of reaction and justify. Okay, so let's call this reaction 1 and this reaction 2. Reaction 1, this is an elimination reaction, and for this alcohol to alkene elimination reaction we're going to need H2SO4, but it's going to need to be concentrated. Okay, so that concentrated H2SO4 that can rip off the water molecules. So we remove H2O, form a double bond. Okay, for the second one, it's an addition reaction. We are using H2SO4 dilute. Okay, and you can sometimes see that written as H plus H2O, so like acidified water. So, same thing. Okay, so that's the conditions. Type of reaction occurring is addition, we've mentioned that. The conditions, we mentioned that. And what's happening, how we justify our choices. Well, an addition reaction, how do we know it's addition? Double bond breaks. It's just the reverse of this one, isn't it? Double bond breaks. And H2O is added. More specifically, one carbon gets OH, one carbon gets H. The two carbons of the double bond, okay? Okay, next question is going to be a flowchart. So we're starting off with an alkene, and so as soon as we see that, we're thinking this double bond is going to be reactive, and it's going to form a major and a minor product here when it reacts with HCl. Okay, so this is an addition reaction, obviously. Now, with the hydrogen and the chlorine being added across the double bond, most of the time the hydrogen will go to the carbon that has the most hydrogens already, and this has 2. So that will happen most of the time. That will be the major product, and the chlorine will go on to the middle carbon. But let's go with the minor product here. So we're going to go H3C, that's that part, single bond to a carbon, which to start with has 1 hydrogen on, and then this carbon here has 2 hydrogens on. So the double bond's broken. We're adding 2 things on. We're adding a hydrogen and a chlorine. The minor product is going to be when this carbon that only has 1 gets the extra hydrogen, and this one gets the chlorine. Okay, so what could we do with alcoholic NH3, alcoholic ammonia? Well, it could do a substitution reaction with this part of the molecule. So there's going to be a substitution. Okay, it's going to take the chlorine off, and the NH3 is going to go on. So it's going to go H3C, CH2, carbon, hydrogen, hydrogen, and NH2 there. Okay, so that's our substitution reaction. Over here, we've got another substitution reaction. This time, we're getting an OH taking the place of the Cl. So what can we do that with? KOH, aqueous, that's important, because remember the KOH alcoholic is going to do a different reaction, an elimination reaction, so this is KOH aqueous, and we're forming an alcohol. Now we've got a different type of reaction with an unknown reagent to get to a carboxylic acid. So an alcohol going to a carboxylic acid, the type of reaction is oxidation. And the reagent, well, there's a few things we can use. I'm going to choose acidified dichromate, Cr2O72-. Acidified dichromate, also acidified permanganate would have worked. Okay, and then down here, sodium hydroxide and carboxylic acid. We're thinking acid-base reaction here, aren't we? So H3C, CH2, carbon, double bond O, single bond O. Now it's acted as an acid and reacted with that to form H2O as water, and it's also formed the propanoate ion, and then of course it's going to be an Na plus there as well. Question 2 is polymer question. This is a Teflon chain, polymer chain, and the first question is to draw the monomer used to make this polymer. Okay, so if it's a monomer, we know it must have a double bond because that's how you make polymers, at least by addition, polymerization. So then we can put a carbon in there and a carbon in there. Now if we were to just cut this molecule like there and there, this is our monomer. So we just chuck one fluorine up, one fluorine down, one fluorine up, one fluorine down. The name of this molecule here is going to be 1, 1, 2, 2, tetra, fluoroethene. 1, 1, 2, 2, 4 is tetrafluoroethene because there's a double bond. Okay, chemical reactivity of monomer and polymer are different. Analyze this. Structure of the monomer and the polymer compared to its reactivity, and the importance for the importance of this for Teflon's use as a polymer. Okay, so the difference is the double bond. Okay, the structural difference of these is the double bond. Now, what does this mean? This leads to reactivity. Now, why is this important? Teflon doesn't have this. Teflon doesn't have this double bond. Doesn't have the double bond, therefore can be used in cookware. Right, you wouldn't want your pans reacting with your food, would you? Especially when you heat them up. Alright, isomers now, A, B, C. Circle the form of isomerism that exists between A and B. Okay, A, B, the double bond here is between the first and the second carbon. The double bond here is between the second and the third. So that's a constitutional or structural isomer. Whereas between B and C, we see that we've got the same positioning of the double bond. It's between the second and the third in both cases. But we've got this cis-trans thing going on here, don't we? So this is geometric isomers. Okay. Compare and contrast these two. A and B have the same atoms, as in same molecular formula. Okay, but they are actually joined differently. As in, you know, this carbon here has got 2 hydrogens attached to it. This carbon here has got 3 hydrogens attached to it. That's the far left side of these molecules. They're joined differently. They're also named differently, of course. And we could say that if we wanted, this is meth, eth, pro, bute. So this is bute-1-ene. This is bute-2-ene. Okay, so we've talked about the requirements, and we've referred to the molecules above as well specifically. Okay, so B and C, these are the same atoms, same molecular formula as well. It's the same, okay, but they're joined the same. But they are arranged differently in space. Now the requirements for that is double bond, and the carbons involved in the double bond must both have different atoms or groups of atoms attached to them. So this has got CH3 and an H, this has got CH3 and an H, this has got H and a CH3, this has got CH3 and an H. Carbons in double bond have different atoms or groups of atoms attached to them. Okay, and then we're going to be specific about this and say they all have CH3 and H. Okay, so these all have CH3 and H attached to them. So let's name them as well. B is on the same side. These are on the same side. So we'll say that this is cis bute. Oh, get rid of that. Cis bute 1-ene. Sorry, I've had a shocker there. Let me just do that again. Cis bute 1-ene, and C is trans bute. Oh, sorry, 2 as well. 2 1, 2 butene. Cis-butene, trans-butene. Trans because they're opposite each other. Okay. Oh, got there in the end. Okay, question 3. When this molecule was reacted with KOH alcoholic and heated, a mixture of products are formed. Okay, we've got a major and a minor again. All right. What's going on here? We need the type of reaction, we need why two products form, and how we know which one's the major and the minor. All right. So, as we said before, when we did this question on the aqueous KOH doing a substitution reaction, alcoholic KOH will do an elimination reaction. It's going to eliminate this Cl, which will form KCl, a salt, and then the OH is also going to react with one of the hydrogens either coming off this carbon or coming off this carbon, and it's going to form H2O. Elimination reaction, you eliminate the chlorine and one of the hydrogens and you form a double bond. The rule for which one comes off depending on the major or the minor product, when the chlorine comes off, one of the adjacent carbons will also lose a hydrogen, and the major product is when the carbon that has the least number of hydrogens loses another one. So if this is the first, this is the second, this is the third carbon. In this case, the major product, the third carbon, will lose its hydrogen. Okay, so we're going to write H3C, CH, double bond. We lost that chlorine to a carbon. That carbon's got a CH3 down there, and then single bond CH3. Okay, so you can see that these two carbons here have the double bond between them, lost this hydrogen here and this Cl. And then the minor product is going to be when the carbon that has the most hydrogens loses another one. So in this case, the carbon, double bond carbon is in the middle, at the start. Put our hydrogens on for that one. This carbon has a hydrogen. This one here has the hydrogen this time because it didn't lose it. CH3 there, and CH3 on the end as well. Okay, type of reaction in both of these cases is an elimination reaction. Okay, it's an elimination reaction because Cl and H removed. Chlorine from that carbon and the H from a neighbouring carbon. Okay. Also, the double bond is formed. Okay, and how do we know which one's the major and the minor? Major, the carbon with the least hydrogens loses another. And then minor is when the carbon with the most hydrogens loses another. Right, so we've explained the type of reaction, how we know which one's the major and the minor, and why there's two products, okay, because the carbon on either side can lose the hydrogen. All right, one of those typical labels have fallen off the bottles. Questions, we need to identify them with some chemistry tests. So we've got a solution of sodium hydrogen carbonate, and we've got three things that we need to identify. Ethanol, okay, so we're thinking this is an alcohol, OH group. Hexene, okay, this is the double bond. And propanoic acid, that's obviously an acid. Okay, so sodium hydrogen carbonate, you should be recognizing that this is a base. This is a carbonate, which is a base, and that's a clue for us. So the acid will react with the base. This is going to react with this. We're going to get a neutralization reaction, and we're also going to get CO2 gas produced as bubbles. Okay, so you need to know that carbonates react with acids to produce CO2. Now we've got two left. How do we identify the ethanol and the hexane? Well, neither of these will react with the sodium hydrogen carbonate, but if I was polar, and therefore will mix with the NaHCO3, whereas the hexene is nonpolar and therefore will not mix and will form layers. Okay, so that will be the chemical reaction, and then this is just a physical property of how we can separate these two out. Okay, explain how you could use an alternative reagent to do a chemical test. So here we've got to have to use a chemical test. We can't do something like layers because that would be a physical property. Chemical test that would allow us to distinguish between hexane and propanoic acid. Alright, so we've got a double bond and we've got a carboxylic acid. So I'm just going to go with the real classic one for a double bond is bromine water, Br2AQ. This is bromine water. That's our reagent. What is the observation? The orange solution will rapidly decolorize. Okay, so that's that orange bromine water turning clear immediately. Observation that, well, with hexene, nothing will happen the acid, so the carboxylic acid is not going to react with the bromine water, it's not going to decolorize it. The type of reaction happening, if you've got a double bond and you're adding bromines in across it, this is addition reaction. And for, I guess, a bonus point, you could say specifically it's halogenation, isn't it? Because you're adding halogens. And that's us.